So now we're going to look at what it actually means for a compound to be aromatic. Now, this is going to be a fairly brief overview of what it means to be aromatic, or what aromaticity means, along with a little bit of history, but it's going to get us to where we need to be. And so one of the questions is, what makes benzene unique? We've seen throughout this course that benzene doesn't behave like an alkene does, even though we often draw it in the same way that we draw alkenes. And so benzene has been known for quite a long time. It was isolated first 1825 by Faraday, and he was able to isolate it from some coal residue. Now, at the time, its structure was not very well understood, and it would take quite some time for that to be determined. And it would be another 40 years before someone really proposed a structure for benzene. And that brings us to 1865 with Kekulé. And what structure did he propose? So he proposed this six-membered ring with 3 double bonds. Now, what was the basis for this proposal? So here's what he wrote as part of his justification. He said, "I turned my chair to the fire and dozed. Again, the atoms were gamboling before my eyes. My mental eye could distinguish larger structures of manifold conformation, long rows, sometimes more closely fitted together, all twining and twisting in snake-like motion. But look, what was that? One of the snakes had seized hold of its own tail, and the form whirled mockingly before my eyes. As if by a flash of lightning, I awoke, and this time also I spent the rest of the night in working out the consequences of the hypothesis." So yes, if you're wondering, basically he said he came up with this structure in a dream. But there was, one major issue here. And the major issue was that even in 1865, reactions like halogenation of an alkene were already known. And so it was known that if you took an alkene like cyclohexene and added bromine to it, that as we learn, in our alkene section, that alkene will react and we get 2 bromines where the alkene was. Even in 1865, it was known that if you tried this same reaction with benzene, it didn't work. And so it was known already that benzene was not made up of alkenes. So that meant this initial proposal couldn't be exactly right. And so at that point, he modified his proposal, saying that instead benzene must be made up of these 2 structures, and that the double bonds were delocalized. Now, here, when we hear this today, this doesn't sound like that novel of a suggestion. But this was 1872 that he suggested this. And this is actually a remarkable idea in 1872, because the idea of a delocalized double bond, well, it turned out the electron wasn't going to be discovered for a number of years after that. So now we know that the structure of benzene is really that those 6 pi electrons are delocalized and shared by the entire ring. So sometimes as you've probably seen. Instead, we'll draw benzene like that to represent that those pi electrons are completely shared. Now, as we've talked about many times in the past, the idea of delocalization, anytime we delocalize electrons, we know that's a stabilizing effect. And that's something that we see very much in benzene. One of the ways we can see that in benzene is through heats of hydrogenation. In other words, what is the amount of heat that, what's the energy difference when we have an alkene and go to cyclohexane? So in the simplest case, cyclohexene being hydrogenated, we get the heat of hydrogenation is negative 28.2 kcals per mole. Now, what happens if we go to two alkenes? Well, if we go to two alkenes, there's two ways that we can do that. We can have the alkenes next to each other, or we can have them separated. When they're right next to each other, the heat of hydrogenation is negative 55 kcals per mole. Not quite double. That's because we gain a little bit of energy from the conjugation there. When the two double bonds aren't conjugated, then it's almost exactly double, having just one double bond. So what this leads us to believe, if one alkene is about negative 28 kcals, two alkenes are about negative 56, three alkenes should be triple that, somewhere on the order of negative 84 or negative 85. But when you try to hydrogenate benzene, which is actually very difficult to do, but it can be done, its heat of hydrogenation is only negative 37 kcals per mole. So not only is it not triple having one double bond, but it's actually less than double. And so we can see that this idea of aromaticity or delocalization of these pi electrons is a hugely stabilizing effect within the ring. Another piece of information that showed benzene was fairly unique from other compounds was the following. If we have cyclohexene and we measure the bond length in cyclohexene, the double bond in cyclohexene measures in at about 1.34 angstroms. The single bond right next to it, much longer as we would expect, 1.54 angstroms. What do we find in benzene? In benzene, all 6 carbon-carbon bonds are exactly the same, and they're about 1.39 angstroms. And so this tells us that, first of all 6 bonds in benzene are the same, but secondly, it tells us that they're not double bonds because they're not as short as a double bond, but they're not as long as a single bond. So the carbon-carbon bonds in benzene are somewhere between a single bond and a double bond. So eventually, by the 1930s, Huckle gave us, what is known as the Huckle Rule, which is how we define aromaticity. And so aromatic compounds are defined as planar conjugated rings with exactly 4n plus 2 pi electrons. And n here is just any whole number. So this could be 2, 6, 10, 14, etc. So any not even non-multiple of 4 counts as an aromatic number of electrons. In addition, again, the ring has to be completely planar, and the ring needs to be fully conjugated. And, importantly, aromatic compounds are compounds that gain stability from delocalization of electrons. Now, what about the other numbers, say 4, 8, 12, 16, the multiples of 4? Well, those fit under the category of anti-aromatic. So anti-aromatic have 4n pi electrons, and they're the opposite. So whereas an aromatic compound gains stability from delocalization, an anti-aromatic loses stability from delocalization. And so it turns out in an anti-aromatic compound, there's no delocalization going on at all because that will actually destabilize the molecule.